Hi, this is Professor Fernandez. We're working on Class Notes B in Lesson 13. So in this class notes, you're asked to find the eigenvalues and the eigenvectors of this matrix. Based off of all of the work we did in the previous video and all the work we've done in the lesson notes so far, we know that the first step is to find the determinant of a minus lambda I and set it equal to 0. That's going to give us the characteristic polynomial. We will find the roots of that to get the eigenvalues. All right, so let's talk about what this determinant of a minus lambda I is. Like we said in the previous video, you take the matrix A and you subtract lambda from the diagonals. Okay, so this first entry of this a minus lambda I is going to be -2 minus lambda. And then here's the other diagonal of the matrix A, so 3 minus lambda. And then I don't change the rest of the entries of the matrix. So I keep the 1 and the -4. Right? And now I'm finding the determinant of this. This is our A minus lambda I matrix. It is a 2 by 2 matrix, so the determinant is just going to be the product of these two entries, so -2 minus lambda times 3 minus lambda, minus the product of the off diagonal entries, so -4, okay, equals 0. And then my job here is to solve this for lambda. So I'm going to multiply things out a little bit. So I get -6 plus 2 lambda minus 3 lambda plus lambda squared plus 4. And then simplify a little bit. Lambda squared. So -3 lambda plus 2 lambda, that's minus lambda. And then -6 plus 4, that's -2, equals 0. And then, by the way, this second degree polynomial is p of lambda. This is the characteristic polynomial for this matrix. So my job now is to solve this for lambda to find the roots of this polynomial. There are lots of things I could do. This is a quadratic equation. I could use a quadratic formula, or I could try to factor, right? So that would be my first suggestion to try. So if I try to factor, then it looks like lambda plus 2, lambda minus 1 is going to work. So is that true? Nope, it does not. I have to switch the signs here. So I have to do lambda minus 2, lambda plus 1. So as a quick check, lambda squared plus lambda minus 2 lambda gets me that negative. And then -2 times 1 gets me that -2. All right, so that works out. So now that I have factored it, I can find my lambda values. So I get lambda equals -1 and lambda equals 2. Great, so I have found the eigenvalues. These are the e-values. How do I find the eigenvectors? Well, I'm going to go back to an intermediate step in the previous video, right? Remember that before we got to this condition, by taking AV equals lambda V, the definition of what it means for V and lambda to be eigenvector and eigenvalues respectively. And we had expressed the equation in this form. It's from there that we then applied the first theorem in this lesson to give us this as a condition for the eigenvalues. Okay, so I'm going to go back to this form of the eigenvector eigenvalue equation, and now this is what I'm going to use, and in general this is what you use to find the eigenvectors. I'm now going to substitute in the first eigenvalue into this equation and find the eigenvector. Then I'll go back and do the same thing for this eigenvector. Okay, so the first thing I'll do here is notice again, this is A minus lambda I. It's the same matrix that we found up here, except I'm not taking the determinant. Right, now it's getting multiplied by V and set equal to 0. Okay, so A minus lambda I. So here it is. I'm going to plug in lambda equals -1 for this in here and also in here. All right, so I do -2 minus -1, and then the upper right component is 1. Then the lower left component up here, -4, and then or 3 minus the lambda value, which is -1. Okay. So I'm going to write this down here, and now I'm solving this system. And the way I'm going to solve the system is using augmented matrices. Right? That makes it a little easier to keep track of what's going on, and it also goes back to very, very early things that we had done in the first, really the first lesson in this linear algebra unit. So to solve this, I'm going to simplify it a little bit. So I get -2 minus -1, so -2 plus 1, -1. And then down here, I get 3 minus -1, so I get 3 plus 1, 4. Okay. And notice, based off of all the things that we talked about in this lesson notes, we should get an infinite number of solutions, an infinite number of eigenvectors. So we are going to pick out one of those to form effectively the basis for the eigenspace. But we're going to pick out one of those as the eigenvector. So in this case, if I row reduce here, you can see that these two rows are exactly, one of them is going to zero out. So I could keep the first row, and then to zero out the second row, I could just multiply the first row by 4 and then add it to the second row, and that would give me all zeros. Okay, and I wouldn't have changed the first row, so I'll keep it that way. All right, if I now write this first equation, this first row as an equation, the eigenvector v here, I'm going to say has components v1, v2. So this first row is minus v1 plus v2 equals 0, which tells me v1 equals v2. So my eigenvector v in this problem, which had components v1, v2, actually the two components are the same. So if I factor out the v1, I get that. And this is what I was saying, just a minute ago. So all of the eigenvectors corresponding to the eigenvalue -1 that we've used are multiples of the vector 1, 1. So we are going to call v sub lambda equals -1. We're going to call the eigenvector corresponding to this eigenvalue 1, 1. Okay. Again, you could choose any other eigenvector, any other vector that's a multiple of 1, 1. You could choose 3, 3, 7, 7, or something exotic like pi, pi, right? It's totally up to you. But because every single eigenvector is a multiple of 1, 1, and 1, 1 is a fairly simple vector, then that is the eigenvector that I'm going to choose for this eigenvalue. So what I'm going to do now is I'm going to erase all of this. I'm going to just record up here that we found this eigenvector. Actually, I'll leave it down here. And I'm going to go back, like I said earlier, excuse me, and do everything all over again for the second eigenvalue. All right. So what's going to change is this matrix, and therefore the row operations, and therefore the eigenvector. So let's go back and redo this calculation for the eigenvalue of lambda equals 2. So I'm going to put it here, right? And then I'm going to redo the arithmetic. So now I have -2 minus 2, that's -4. Keep my 1, -4. And then 3 minus 2, that's 1. And so again, you can zero out this second row by just multiplying the first row by -1 and then adding it to the second row. And that leaves this first row. So if I take this row and write it back out as a system, minus 4v1 plus v2 equals 0. I will confess I have a little bias against fractions, so I am not going to solve for v1. I'm going to solve instead for v2. So v2 is 4v1. So therefore the eigenvector v, which had components v1, v2, now looks a little different in this case. It has components v1, 4v1. So if I factor out the v1, I get 1, 4. And like we did before, I'm going to call this the sort of generator of the eigenvectors corresponding to the eigenvalue, lambda 2 equals 2. So that's 1, 4. Okay, so that is how you find the eigenvalues and the eigenvectors for this example. Quick little recap, right? Two-step process. Here it is. First one, find the eigenvalues. You do that by subtracting lambda from the diagonals of the matrix, calculating the determinant, setting it equals 0, solving for the lambda values. Great. Now, once you have the lambda values, go back to that A minus lambda I matrix you calculated, substitute in the lambda value you have, row reduce, and then figure out what is, pick one of the vectors that results as your eigenvector. You will have lots of choices, right? But if you do the math in this fashion that I have illustrated, you'll end up with what I'm going to call a natural choice for the eigenvector. And then you go back and you do that repeatedly for however many, that process for however many eigenvalues there are. And that will generate the pairs of eigenvalues and eigenvectors.